In this video, we solve problem 1 of unit 15. In this problem, we have two charges, Q1 and Q2, that are here marked, that are moving towards the right, the first one, and towards the left, the second one. So we have that Q1 is equal to 1 microcoulomb, Q2 is equal to 2 microcoulomb. The speed of the first one is 10 to the 6 meters per second. The speed of the second one is twice this amount. At an instant, they are both at a distance, I call it r, equal to 2 meters, and this is 0.5 meters, okay? We're going to call theta this angle, which is the same angle, and we can see from the drawing that the sin of theta is going to be equal to 0.5 divided by r, which is 2 meters, which is 0.25. So the cosine of theta is going to be the square root of 1 minus the square of the sin, which is 0.25 square, which is 0.968. Then in the section A, they want us to calculate the electric field and the magnetic field provided at the point where the second charge is and generated by the first charge, okay? So for that, we're going to need Coulomb's constant, which is 9 times 10 to the 9 Newton square meter divided by square coulomb, and we're going to also need mu sub 0, which is 4 pi 10 to the minus 7 Tesla times meter divided by ampere. Okay, so we begin in section A by calculating the electric field provided by point charge 1 on the place where we have point charge 2, okay? This we denote by this. And this is going to be equal to K Q1, because Q1 is the charge that is providing the electric charge, divided by the distance between both, times the unit vector that goes from one to the second one, okay? So here we know that this distance is directly what we've called r, which is 2 meters. And then to decide what is this unit vector, we have to see that r from 1 to 2 is this vector with this direction, okay? So the unit vector is going to be equal to the cosine of theta in the direction of x minus the sin of theta in the direction j. Okay, we already derive which are these quantities. So putting everything together, we see that because we have K and we have Q1, this vector, this electric field, is going to be equal to 2178 unity vector in the x direction minus 562.5 in the y direction. This is Newton divided by Coulomb or volts per meter, as you prefer. Okay, and in the drawing, this electric field has this direction. Okay, this is one, 2. Then to calculate the magnetic field, we need to use this expression, which you can find in the books or in the previous video or in the slides. This is 4 pi mu sub 0 divided by 4 pi times Q1, because this is the magnetic field exerted by 1 on the place where I have the second one, okay, times the speed of the first one, the cross product with the unit vector that goes from the first to the second one, divided by the distance between both. Okay, here we have again this and this. Okay, so here we can discuss first the direction of the magnetic field, which if you see, the unit vector is going to have this direction, and the speed has this direction here. So they both belong to the plane of the screen, so the magnetic field has to be perpendicular to this plane. So it has to be either into or out of the plane, okay? If what we are using is, this is y, this is x, so z would be the axis that goes out of the screen. So magnetic field is proportional, it has the same direction as the cross product between this velocity v1 and the unit vector in this direction. So to get this cross product and to know if the magnetic field is going out or in, we have to get in the index the velocity, in our middle finger the unit vector, and so we are left with our thumb pointing into the screen. So that we represent as an X in this place. So the magnetic field is going to go into the screen. So this is the magnetic field is going to be equal to mu sub 0 4 pi q1 divided by r1 to the square times v1 times the unity vector, the modulus of the unity vector, times, which is 1, we know already, times the sin of between the sin of the angle between both, which is theta, and this has to be multiplied by minus k, because we've just derived that this has to go into the screen, and so that's how I derived this direction, okay? So the rest is just a matter of multiplying, because we have everything. So this, remember that this is 1, okay? So we have the rest of the things. So if you multiply all of them, you end up showing that this is minus 6.25 times 10 to the minus 9 K, okay, Tesla. Okay. So in the second section, they're saying that as there is an electric and a magnetic fields applied where the second charge is, we can calculate the total amount of force exerted on this charge. So the total amount of force, let's call it total, provided by 1 and exerted on 2 is going to be the part that comes from the electric field, okay, plus the part that comes from the magnetic field, okay? So the part that comes from the electric field is just Q2, which is suffering the force, times the electric field provided by 1 where the second one is. So this is just a matter of multiplying this expression here by the charge of the charge of the second one. So this is directly, if you do the calculations, 4.35 in the x direction minus 1.125 in the y direction, and this is in millinewton divided by, excuse me, this is 10 to the minus 3 Newton directly. Okay, so now for the magnetic field of 1 exerted on the second one, this has to be equal to the charge of the second one times the speed, the velocity of the second one, the cross product with the magnetic field generated by the first one on where the second one is. So first we can discuss, if you want, the direction of this force. So this direction of the magnetic force is going to be perpendicular to this, to both the velocity and the magnetic field. So as it is perpendicular to the magnetic field, it has to be, it has to belong to the plane of the screen. And as it is perpendicular to the velocity of the second one, it has to be in the direction of the y-axis, okay, so in this direction. And just to provide, if it has to go towards up or left or down, we just have to use the right hand rule. So for the right hand rule, we put in the index the velocity of the second one, and then in the middle finger the magnetic field provided by the first one where the second one is, that was a vector that was going into the screen. So the thumb leaves you pointing towards this direction. Okay, so this is minus j. Okay, and then the rest of the magnitudes, you know them all, because we know Q2, we know V2, and we just calculated up the magnetic field. So if you multiply everything, this is equal to minus 2.5 times 10 to the minus 8 in the k direction, and this is in oh, sorry, no, I think I'm sorry, I'm copying something that is wrong. So again, so this force is, sorry, minus 2.5 times 10 to the minus 8 in the j direction, and this is in Newton. Okay, so the total force that is the addition of both is approximately equal to the electric one, because the magnetic one is much smaller than the electric one. Okay, so here you have it. Now we're going to solve the other two sections. These are sections C and D, which ask you to calculate the same, the electric field and the magnetic field, but this time those that are created by the second charge where the first charge is. So I'll pass to another page to calculate this. So in C, we want the electric field provided by the second charge on where the first one is. So this is equal to K times the charge that is generated, which is Q2, divided by R to 1 to the square, R to 1, the unity, the direction of the unity vector. So we already know that R to 1 is the distance between charges, which is R, which is 2 meters. And here we have to discuss which is this direction. So if you remember, we had the first charge here, and then we had the second charge here. So now this vector is going to be this one. This is R2 going to 1. So as we said, this is theta. Now this unity vector has to be equal to minus cosine of theta in the x direction plus sin of theta in the y direction. Okay, so if you put everything together, and as we know already the different amounts, this electric field provided by the charge 2 where the first charge is minus 4,357 plus 1,125 J, and this is in Newton divided by Coulomb. Okay, for the magnetic field of created by the second charge where the first charge is, this is equal to mu sub 0 divided by 4 pi times the second charge, which is generating the magnetic field, times the velocity of the second charge, the cross product with the unity vector that goes from the second to the first one, divided by their distance, the square of the distance. Okay, so here we have to discuss the direction. So we see that V2, which is this vector, this is V2, and R21 are both belong to the plane of the screen, so the magnetic field has to be perpendicular to the plane of the screen. And to know if it's going to go into the screen or out of the screen, we use the right hand side rule, where we have to place in the index the velocity of 2. In the middle finger we have to place the unity vector pointing from 2 to 1, and so our thumb is left pointing into the screen. So this we would represent with an X here. So that would be B of 2, 1. This is the magnetic field created by 2 on 1. So that is, this is a direction that goes with minus K. Okay, so we already have the direction, and now we just have to multiply everything. So this is mu sub 0 divided by 4 pi, this is q2, this is v2, this is r to 1, but we know that already that this is r, which is 2 meters, and then here we have to multiply by the sin of the angle that v2 and r to 1 form, which is theta. So we have to multiply here by the sin of theta, okay? So if we do all this, we end up showing that v to 1 is equal to minus 2.5 times 10 to the minus 8 in the k direction, and this is in Tesla. Okay, so in the last section, they're saying, okay, as you have an electric field and a magnetic field where the first charge is, calculate the total force exerted by these fields on it. So we have that the total force exerted on 1 because of 2 is going to be the part that comes from the electric field and the part that comes from the magnetic field. Okay, so the part that comes from the electric field is just going to be the value of the second charge times the electric field where this is the charge of the first charge times the electric field provided by the second charge where the first one is. This is just multiplying this here by Q1, that was 1 microcoulomb. So if you do this, you can show that this is going to be equal to 4.35 in the x direction with a minus here, because we had a minus here, plus 1.125 in the j direction, everything multiplied by 10 to the minus 3, and this is Newton. Okay, so I want you to go back, if you can, and see that this force is exactly the same magnitude but just opposite to what you had in exerted on charge 2. So you had that on charge 2 you had this force, okay, and in charge 1 you're going to have this electric force. So they both have the same direction but opposite direction, sorry, and they have the same magnitude. And this is an example of action-reaction pair. Okay, so this is a force of interaction between two charges. Okay, this is the electric part, so they are equal but just have opposite signs. In this case, as they are both positive, they have both the same sign, the charges, the forces repel, and the charges repel each other. Okay, so just check that this is just the same but with the opposite direction as so F to 1, the electric one, is equal to minus F1 to the electric one. Okay, on the other hand, the magnetic part is going to be given by the first charge times the cross product between its velocity and the magnetic field exerted where this charge is. Okay, so again we can discuss this cross product, and as you see, V1 belongs to the screen plane, while the magnetic field was perpendicular. So this cross product is equal, its magnitude, to Q1 times B1 times B21, okay, and the direction has to be perpendicular to the velocity 1. So the velocity 1 was in the x direction, so this has to be in the j direction, in the y direction. Okay, so I put that there a j, and now we can discuss what is going to be the direction. Is it going to be positive or negative? So to know that, we use the right hand side, the right hand rule. Okay, so we place the first velocity, the velocity of 1 in the index. We place we place we place, the velocity of 1, okay, so yeah, in the index, so it's going to the right, and then we place the middle finger pointing into the screen, so our thumb is left pointing in this direction, okay? So this is the force, the magnetic force exerted by the second one on the first one, which is, then this is plus J, okay? Because we've discussed it. So if you just calculate it, this F21, the magnetic one, is going to be equal to plus 2.5 times 10 to the minus 8 J in direction, and this is Newton, okay? And here I want you to realize again that this F21 magnetic is equal to minus F12 magnetic, because this is another pair of forces. It's the interaction between two bodies, okay? So at the end, the total force exerted by 2 on 1 is approximately equal to the electric part, because the magnetic part is very, very small, okay? In any case, what you have is the total force of 2 on 1 is equal to the minus total force of 1 over 2,